Welcome back to the next video, everybody. Today we're going to spend a little time formalizing the R equals T problem and just kind of being clear about what it is that we're trying to prove. So let's do that. Here's the setup. We're going to fix a continuous representation rho bar from GQ to GL2 of K, where K is a finite field of characteristic L. We're going to assume L is odd, that rho bar is irreducible, that rho bar, when restricted to the local inertia group at L, is flat or ordinary. In other words, rho bar is semi-stable at L. That rho bar has cyclotomic determinant, and that rho bar has square-free conductor. Because remember, we're just really trying to prove the semi-stable modularity theorem, and elliptic curves have square-free conductors. And it just makes the proof easier. Okay. So speaking of the double, if EQ is a semi-stable elliptic curve, we saw in chapters 1 and 2 of this playlist that rho bar EL, the residual mod L representation attached to E, satisfies these conditions as long as it's irreducible. By Mazur's isogeny theorem, this will be the case, for example, if the prime L is bigger than 7. Okay, and then we're going to put one more assumption on rho bar. So we're going to assume rho bar, crucially, is modular. Namely, let's be precise about what we mean and recall what that means. Let's fix embeddings of Q bar into Q bar L, Q bar into C, and K into F bar L, where F bar L is the residue field of the ring of integers of Q bar L, the algebraic closure of, or an algebraic closure of the L-adic numbers. We'll suppose that F is a weight 2 new form of level NF and trivial character, and we'll let K sub F denote the number field generated by the coefficients A sub n of F of the new form. The chosen embeddings determine a prime lambda over L of OF. We talked about this way back in chapter 3, where OF is the ring of integers of K sub F. We'll shorthand and write rho sub F for rho sub F lambda, which is a construction we're familiar with. It's the absolutely irreducible L-adic representation attached to this F and this prime lambda from GQ to GL2 of KF lambda. And it's characterized up to isomorphism by the property that if P is a prime not dividing the conductor N sub F times L, then rho sub F is unramified at P. Trace of rho sub F of Frobenius at P is nothing but the Pth Fourier coefficient of F. And the determinant of rho sub F of Frobenius at P is nothing but P. Okay, so this was all dealt with back in chapters 1 and 3 of this playlist. Okay, so what do we mean? Well, we recall that we can choose a basis that the image of rho sub F is actually contained in GL2 of O sub F lambda, not just K sub F lambda. This was dealt with in chapter 3 as well. Recall also that the reduction rho bar F from GQ to GL2 of OF mod lambda is well defined up to semi-simplification, and this is sort of the residual semi-simple representation attached to F. Okay, so what we're assuming is that our given rho bar is equivalent over F bar L to rho bar F for some weight 2 new form F in the above sense. That's what we mean by rho bar is modular. Okay, it turns out that once we can impose this condition, there are infinitely many F we can actually choose from by Ribet's results in his congruence paper. If I give you a finite set of prime sigma, we can ask which of these F actually give rise to a representation of so-called type sigma, which you might recall from the previous video means that rho bar F lambda is semi-stable at L, and sigma contains the set of primes dividing the conductor of rho F lambda divided by the conductor of rho bar. Okay, so again, like this, the infinitude here is kind of a problem. This is why we have to change the R equals T problem and make it an R sigma equals T sigma problem, which we're going to describe right now. Okay, a sufficient condition for F to be such a new form is that NF divides the quantity that we'll call N sub sigma, which is N of rho bar times the product over primes and sigma of P to the M sub P, where these M sub P's are as follows. M sub P is 2 if P doesn't divide N of rho bar L. M sub P is 1 if P doesn't divide L and P divides N of rho bar. M sub L equals 1 if rho bar is flat and ordinary at L. And M sub L equals 0 otherwise. We're not going to heavily leverage this fact, but this is a good thing to know. If you want a proof of this, you can see Gouvea's deforming Galois representations controlling the conductor. I guess I'll call it a paper. It's quite long, though. Okay, now, so where are we headed with this? Again, I want to formalize the R equals T problem. What do I mean by proving R equals T? Let's let phi sub sigma denote the set of new forms f of weight 2 trivial character and level dividing n sub sigma. So it's exactly the f's that we want, basically, according to the above setup. As explained in chapter 7 of this playlist, phi sub sigma is non-empty, and of course, an analogous result holds for each phi sub sigma automatically. Okay. So these sets, they actually have things in them. All right. So let's consider the ring T tilde sub sigma, which is the product over F and phi sub sigma of the number rings OF lambda. All right. The reason for this notation is it's suggestive that this is going to be a Hecke algebra, and it is. Okay. So let's recall for each F, the prime lambda of K sub F is determined by our choices of embeddings. Okay. And let's note also that T tilde sigma is semi-local and it's finitely generated as a ZL module. These are just good things to know. Okay. For each prime P not in sigma, let's let T sub P denote the element. We're going to make like a sequence that runs over all F and phi sub sigmas of the AP of F's. Okay. So the reason we're calling this T sub P is this looks very much like something a Hecke operator would do. We know Hecke operators are often acting as multiplication by APF. We'll define the Hecke algebra T sub sigma as the Z sub L subalgebra of T tilde sigma, generated by the Hecke operators T sub P for primes P that aren't in sigma and that aren't L. So remember, the point of introducing these auxiliary sets is we want good behavior away from sigma, and then we've never kind of historically cared, so to speak, about what happens at the prime L itself. So we're throwing all that out. We're looking at the Hecke operators for the remaining primes, and we're calling T sub sigma the ZL subalgebra generated by them. Okay. Now we appeal to Mazur's deformation theory of Galois representations, which was the topic of chapter 8 of this playlist. We're going to keep all the technical conditions imposed on rho bar except the modularity, and we're going to consider deformations of rho bar of the form rho from GQ to GL2 of A, where A is now just an arbitrary complete local Noetherian ring with residue field K. We're going to say more broadly, and I think a little bit more intuitively, that rho is type sigma if all of the following hold. Det rho is cyclotomic. We always want that. Rho is flat or ordinary at L. We still want rho to be semi-stable at L. And then, again, here's this whole, like, we want good behavior outside sigma thing that I've been talking about for 2 videos now. Let P be a prime not in sigma. Then, I want to make sure that if P isn't L and rho bar is unramified at P, then so is rho. Unramification should lift. If P isn't L and rho bar is ordinary at P, so is rho. I want ordinariness to lift. Okay, I want all the good properties to lift. More generally, Wiles considers the so-called type A representations, and we want rho bar. If rho bar is type A at P, then so is rho. And type A just means maybe you don't look exactly like this on inertia, but maybe there's some unramified character chi such that you look like this. Okay, but we're just going to say ordinary here. And then finally, if P is L and rho bar is flat, then so is rho. Remember, flat is kind of the analog of unramification at the prime L itself. This is what type sigma is going to mean for us. This is a broader definition than the one we've already given. And I prefer this one, honestly. Okay, so you can check this is an actual deformation condition. Okay, and so it makes sense to use the results in chapter 8 to find a ring R sub sigma and a universal type sigma, universal deformation rho U sigma from GQ to GL2 of R sub sigma of rho bar. Okay. Yeah, we checked carefully in chapter 8, actually, if you go back and look, that all of these things together do form what Mazur called a deformation condition. Okay, so we have a universal deformation ring attached to the set of prime sigma, and that gives us a universal deformation. Okay, now bring back in the modularity condition. Suppose that rho bar is modular. For each new form F in phi sigma, let A sub F denote the subring of OF lambda consisting of what we care about, the elements whose reductions mod lambda are actually in K. Okay. Recall that with respect to some basis, there is a type sigma deformation, rho F from GQ to GL2 of A sub F of rho bar. We actually kind of just got done talking about that. But again, it's chapter 7 for the case sigma equals empty set. And if you go back to my last video, you might recall that this chapter is trying to reduce R equal T to the empty set case anyway, which we'll prove later. And so this is enough. Okay. Okay. So we have kind of a modular deformation of rho bar. That's what we wanted. The universal property of R sigma, if you recall, gives a unique ring homomorphism, which we'll call pi f sigma from R sigma to AF, such that the composition GQ to GL2 of R sigma to GL2 of AF is equivalent to rho f. So rho f just goes here, and we're just saying this composition is equivalent to it, it's isomorphic to it. In chapter 9, we saw that R sigma is topologically generated by the traces of the rho u sigma of Frobenius at P for P outside sigma and not L. Okay, and so that allows us to conclude that the image of the map R sigma to T tilde sigma, and what is this map? This map sends R to the kind of sequence over F in phi sub sigma of the pi F sigmas of R. The image of this map has to exactly be T sigma, where T sigma, remember, is the subalgebra here generated by the Hecke operators at indices outside this set here. The reason this is true, by the way, is again because this guy's topologically generated by the traces. Okay, but if you just go back, remember this is modular. Okay, this is rho sub f. It's isomorphic to rho sub f, and the defining trace property of the Galois representation attached to this f is that the trace of Frobenius is equal to a sub pf. Okay. But the a sub pf's running over f and phi sigma are exactly the TPs, which generate this Hecke algebra. That's why the image of this map is T sub sigma. Okay? And so what I'll do is, well, what does that give me? That gives me now a surjective ring homomorphism, R sigma to T sigma. Okay? And so where am I headed with this? Where do you think I'm headed with this? Conjecture 1, no matter what sigma is, phi sigma is an isomorphism. This is the R equals T problem. If we can solve this, we're more or less done proving semi-stable modularity. Okay. Why? Let's recall the big picture. Why are we done? We're actually not quite done. There's a few nuts and bolts and loose ends to tighten up. But theorem, suppose that conjecture 1 holds and that E over Q is an elliptic curve with square-free conductor n sub E, i.e. assume E is semi-stable. If there is an odd prime L such that rho bar EL is irreducible and modular, then E is modular. Okay. What does the proof look like in this kind of fancy newer R equals T language? It's actually quite short. Under these additional hypotheses, rho bar EL satisfies all the conditions from the main theorem in this video. I mean, we're given 2 of them, and the other ones were checked. The other ones were checked in like chapter 1 and 2 of these notes. Another thing that we checked also in chapter 1 and 2 of these notes is that rho EL, the actual L-adic representation attached to E, is a deformation of rho bar EL of type sigma for some sigma. In fact, you can just take sigma to be the set of primes dividing n sub E, the conductor of E, times L. Okay. I mean, if you go back up and look at the main theorem, let me just make sure we did cover all this stuff for sure in chapter 1 and 2 for representations attached to elliptic curves. But what I'm saying also is that rho EL is a deformation of rho bar EL of type sigma if sigma is the set of primes not dividing NE times L, okay? Which means we have all of this stuff. And I do distinctly remember covering all this stuff in either chapters 1 and 2 or both of this playlist. Okay, so we've done a lot of the work already. That's the point. All right, so we have all that. So now just take O to be ZL, the L-adic integers. That gives us a unique homomorphism theta from R sigma to Z sub L, where the trace of rho U of sigma of Frobenius at P maps to AP of E. Remember, AP of E is P plus 1 minus the number of FP solutions on E, or more precisely on its reduction mod P, for P naught equals L in sigma. For this, you can just, we've talked about this before, but you can also remember to just see theorem 9.41 in Diamond and Sherman. Again, the point is this is generated by traces of Frobenius of the deformation, right? It'll go to where a trace of rho of Frobenius at P is for the representation rho EL attached to the elliptic curve. But this theorem says that that's exactly APE. Okay, This is kind of a well-known property that we've certainly talked about before for L-adic representations attached to elliptic curves. Anyway, okay, but the conjecture that we're assuming, remember, we're assuming conjecture 1 holds. It says that phi sub sigma is an isomorphism. So you can now look at the composition from T sigma to R sigma to Z sub L, where the composition is theta composed with the inverse of phi sub sigma. So you have a map here now. Okay. From the definition of T sigma, though, this homomorphism has to be a projection pi f sigma for some f in phi sigma. Remember, like ring maps out of T sigma, they correspond to new forms. This is something we've known again since chapter 3. Okay. And because this is T sigma and not just like a full Hecke algebra T, we're actually looking at some new form specifically in phi sub sigma. All right. Well, then trace of rho sigma Frobenius at P has to be APF for these same primes, right? So then APE has to be APF for the primes not in sigma, but that's enough to guarantee that E is modular. I mean, this is a finite set, right? So the L functions agree at all but finitely many places. And so in fact, they'll agree everywhere, which is actually hard to prove, but we don't need it anyway. The definition of modular was, it's okay, it's enough for these guys to agree outside a set of finitely many primes. All right, so that's how you prove most of Fermat's last theorem given, or sorry, that's how you prove most of semi-stable modularity given R equals T. There's a little bit more after this. You have to then make sure that this condition is satisfied. There is an odd prime L such that rho bar EL is irreducible and modular, but that's the so-called 3-5 switch, the 3-5 tricks to get that. That's kind of a quick argument. We've talked about that before in chapter 2 of my notes. We're also going to be talking a little bit more about that later anyway. But now we're kind of set up for R equals T. We're going to start next video proving it in the general case. Okay, so we're going to try to reduce down to the minimal case. That is, we're going to assume the minimal case sigma equals the empty set and prove the general case of R sigma equals T sigma. Thank you for watching, and I'll see you guys then.